So I will first start with a short introduction in how we can express color. So most of you might be familiar with the RAL Classic color standard, which is basically an arbitrary collection of colors used in architecture. It, however, offers quite a limited selection, and the colors in this color space are not very well spaced. So this means we cannot express all colors we observe in nature. Secondly, you might also be familiar with digital color spaces like RGB and CMYK color spaces, which are used in screens, digital representation, and printing. These color spaces are either additive or subtractive. However, they do not cover the full color spectrum. Again, we cannot express all the colors we can see with our human eyes. Finally, we come to more technical color spaces, which were developed by the International Lighting Commission. And these are basically device-independent color spaces, which means no matter where we measure them, they are always fixed in their dimensions. And the two main color spaces here are the XYZ color space, which is basically based on human vision, so we can express all the colors we can see with our eyes. And the LAB color space, which is basically an extension of the XYZ color space to be more perceptually uniform. Why do we need that? Well, we can use it to express color differences. So if we look at two materials of different colors, we can then express the color difference. Okay, so if we know in what space we want to represent our color, we also have to think about the parameters. So the first parameter is hue, or more commonly known as the color tone. This color tone is usually represented on an angular scale, so in degrees, and it is mainly determined by the dominant wavelength of the light reaching our eyes. Secondly, there's a parameter called lightness, which basically gives us the degree between black and white. It's also known as the color value, and it's the relative brightness of a certain sample. It's usually given on linear scale from 0 to 100, and here you can see some examples of how different colors with different lightnesses look. Finally, we come to the color fullness, and here we actually have two parameters. The first one, chroma, is the more natural understanding of color fullness, and it basically compares a color of a certain tone and a certain intensity to a gray sample of equal lightness. And secondly, we have the saturation, which is a different measure of the color fullness, where we compare the chroma and divide it by the lightness. Here in this bottom graph, you can see different shades of blue, which are given on a chroma and lightness scale, and the red lines exemplify colors of similar or identical saturation. So you can see how the colors change with lightness and chroma. Okay, now that we know how to express colors, let us look at the Copenhagen International School you might all be familiar with. As we know, this building exhibits a very apparent angular perception. So depending on which angle we look at it from, we can see different colors. And if we ask the question, what color is this building now, or what color are the PV cells, it's very difficult to find an accurate answer. That leads me to my simple conclusion: a single measurement of the color here might be insufficient. So what can we do? Well, there is something called a BDRDF, which stands for bidirectional reflectance distribution function. And it's basically a complicated formula correlating the reflected light at a certain incidence angle and view angle with the incident light on our sample. We can measure that by using a gonio-reflectometer, which is basically a setup where we shine collimated light, so directed light, on a sample, which can freely rotate. In addition, we have a sensor freely traveling around our sample, measuring the reflected light. And by combining an incident angle, so the rotation of our sample, with a view angle, so the rotation of our collimator or sensor, we can then correlate both incidence angle, view angle with the color appearance of our sample. And here you can see some examples of what we obtain with these measurements. Well, what can we do with these measurements? We can use some color matching functions, these XYZ functions, and some reference spectra, as you can see down here, of a white sample or of the daylight illumination, to convert these into color representations of our samples. Here I'm showing two examples. The first one is a polar plot of a red colored sample, and the lower part is a plot in the LAB color space of the same sample. In the top graph here, you can see the incidence angle on the lower scale, and you can see the view angle on the polar graph. As we can notice here, we have some missing points, which indicate where we have our light back reflected from our panel, because our sensor is blocking the incident light. On the other hand, we also have some white-looking spots. These happen where we get the specular reflections from our sample, so the mirror-like reflections from the surface. I will come back to those in a second. And if we look at the LAB graph, here the main figure of merit is the closer our points are clustered together, the more uniform the sample appears from all angles. Additionally, we can see all the parameters I described before in this graph. The vertical axis is the lightness, giving us the degree from black to white of our color. The distance from this vertical axis is the chroma, or colorfulness, and the orientation in this graph on the AB plane gives us the hue of our color. I also mentioned these white points in the graph up here. Well, these, as I already mentioned, correspond to the specular reflections, and we can use them to determine the glare of our samples. So what do we mean with glare? Well, it's a phenomenon caused by specular reflections, basically where our incident light is reflected like a mirror from our sample, instead of having a very diffuse reflection. It's a property of the surface glazing, so mainly the top surface of our sample determines how much glare we get. And it can of course cause discomfort or even dangerous situations, if we just think of traffic when a driver is confronted with shining light from the surroundings. However, there is a severe lack of regulation standards concerning the glare from PV modules. However, there are some regulations that prohibit glare, especially in urban situations. So that's something we have to consider so we do not end up with situations like this, where we get very shiny reflections, which might cause issues in our urban settings. Okay, before I come to our results of the measurements we performed, I would like to show you the 3 different technologies we investigated. The first one uses a ceramic ink which is printed on the inner side of a glass surface. This achieves coloration through pigments which absorb the color, as Sune mentioned before. Then we have these structural colors, which use a thin film interference coating on the inner side of the glass, as well as an anti-reflective coating or treatment which diffuses the light somewhat. These samples are the samples you might know from chromatics and are also used in the Copenhagen International School. And finally, we have some experimental samples provided by the Solenergie, which basically use a colored layer between the encapsulant between the surface glass and the cells. Okay, now on to some results. First of all, these are the results for the samples with the ceramic ink printing. We can see here in those 2 graphs on the top and also in the graphs at the bottom that the points are very closely clustered together. We have a very uniform appearance over all angles. This results in a very pleasant appearance. However, we can also see that there are some very significant specular reflections signified by these white points in the top graphs. These represent glaring situations due to the smooth surface glass, and they can be a hindrance for this technology. If we now look at the chromatic samples, so structural colors, here we see a completely different situation. We go from very low lightness, so very dark measurements, to very high lightness measurements, which also shows significant color saturation for both samples. Here we see a gold sample, here we can see a blue sample. Additionally, in the right graph, we can see a change from more bluish color at normal incidences to a more violet or magenta color at high incidences. And we could, for example, also see that in the case of the Copenhagen International School, where the change was sometimes towards the violet, sometimes more towards the green. You can also see the same phenomenon on the lower scale here, where we can see a very large spread of points on the AB scale, on the AB plane, which also signifies this change in color, or also called iridescence. Regarding the glare, we can see no significant specular reflections from our surface glass, so they are less glaring situations. However, at these very high view angles, we can still see some white points. And these represent forward scattering effects, basically edge bleeding effects, and we cannot discount those completely. So these might cause, in special situations, also discomforting glare. And finally, we come to the samples with the colored interlayers. And these show somewhere intermediate appearance between those two technologies I presented before. So we can see a relatively uniform across all angles. We do not see any iridescence. However, we see some slight changes in lightness and color saturation. Additionally, we can see again the surface bleeding effect as we saw in the chromatic samples, which might cause reflections at very high view angles. Finally, I would like to also focus a bit on performance. In addition to all these BDRDF measurements for visual characterization, we also performed standard IV flash tests of these samples. As one might imagine, since the first group of samples with the inkjet printing use absorption through pigments, which might not be necessarily optimized for PV applications, these achieve the lowest transmission and therefore the lowest efficiency. In turn, the very well optimized thin film coatings from chromatics, they achieve a very high efficiency. However, as I mentioned before, that comes the trade-off of having a very iridescent behavior and highly diverse angular appearance. Finally, if we look at the samples from the Solenergie, I have to mention these are some samples under development, so might be improved, but still we can see a performance of about 80%. So we have currently about 20% loss. However, this is already very good, since if we compare it to red colored samples, this is the most difficult color to achieve in commercial applications, since the red color is the one which is most significant for PV production. Okay, so this brings me already to the conclusions of my talk, which are basically these 4 takeaway points. So a single angular measurement can be insufficient for the description of BIPV appearance. Secondly, we always have to consider glare, as that might cause problems in our day-to-day installations. Thirdly, that the three different coloration techniques I presented today show vastly different appearances. We can either have an iridescent appearance, or we can have a very common appearance over all angles. And finally, there is always a trade-off between the coloration and the performance. So the appearance is somewhat also at an inverse standpoint towards the performance, with very low performance for uniform appearances and a higher performance for the more angular dependent appearances.